All right, so welcome back. So in the previous lesson, we had a look at some trigonometric integrals where we had computed the different types of trigonometric integrals. Sometimes you'll have a product of trigonometric integrals. Sometimes you'll have some number, odd powers, even powers of trigonometric integrals. So we had to look at three specific cases. One in which we had to look at when we have this type of integral, and we had to look at three specific cases where, for one, we let m being odd, the second being n being odd, and then the third one we had to look where m and n are even. All right, so that's for the first case. For the second case, we had to look at what happens when you have tan and secant as a combination or as a product of each other. So we had to look at what happens when the exponents here are even, and we also had to look at what happens when the exponents here are odd. So then we had generalized two rules for when n is even and when m is odd. All right. And then we also had to look at the third rule where we had to look at a compound angle that involves larger compounds angles in here. So this is the quadruple angle, quadruple angle and the quintuple angle formula. So whenever we had the integral of this form that we have written down over here, then there are three identities that we would use to actually evaluate these integrals. So for one, we had to look at so this identity for whenever we have sine A cos B. For the second one, we had sine A sine B, which gives this identity here. And then the third one, we had cos A cos B, which gives this formula. And as an exercise, I asked you guys to prove these identities. So hopefully you guys tried them. And as well, we also had to look at some techniques of integration practice exercises here. So these ones have been covered in the last lesson in the second half of it. So if you guys want to go ahead and review how I processed and how the steps are done, then just feel free to go ahead and check out that video. All right. So in this lesson here, we're going to be focusing first on the trigonometric substitution. So sometimes when we integrate, we must make a substitution for x. Now, remember last time we did a substitution that involves a u substitution, right? This is for the function. But now we want to, so this is before. But now what we want to do is substitute for a x value such that we get a function that is of f theta, where theta is going to be the angle. So let's start with an integral for which we do not know the answer to just yet. All right, so let's start by making a substitution here. Now, although this substitution may not look obvious, we're going to have to make a substitution for x. All right. So let's say we let x be a sine theta, and you'll see why. Now let's say, well, we're going to have to draw a right angle triangle. So draw a right angle triangle with the theta as the acute angle. All right, so that means, well, here on the left-hand side, if this is your right angle triangle, then what we could say here, well, if we have a look at this trig formula over here, so we have the sine x is equal to a sine theta. Well, sine theta here then is going to be x divided by a. So remember that sine is defined as the opposite over the hypotenuse, right? So that means if this is our angle theta here, this over here is the opposite is going to be x. A is going to be the hypotenuse. And if we use Pythagorean theorem, then this is going to be the square root of a squared minus x squared. All right. Also, we could also make an observation that, well, theta here is just going to be the sine inverse of x divided by a. All right, so let's have a look at the following question. So the question here is, for the function 1 divided by square root a squared minus x squared, what is the domain? In terms of x first. All right. So if we want to know what the domain is, first of all, observe that the denominator can only be ranging from negative a to a, not equal to a. All right, so that means, well, x here has to be between, so we know that x has to be between a or negative a and negative a. But since x was, we set that equal to a sine theta, so that means negative a and less than a sine theta, which is less than a. Let me move this and this arrow here. And so if we divide both sides by a, what we get is negative 1 less than sine theta, and that's less than 1. So that means if we take the sine inverse on both sides, or all three sides here, then we see that, well, the sine inverse of negative 1 is less than theta, which is less than the sine inverse of 1, which then turns out to be negative pi over 2 less than theta less than pi over 2. So I didn't bother going through the 3 pi over 2, so it's better if we go backwards on the axis a little so that we can actually end up with a negative pi over 2 instead. So I'm going to be focusing on this interval here. So this is from negative pi over 2 to pi over 2. So this is the region that I actually want to focus on the number line. All right. So let's have a look. So if we substitute x for a sine theta and we put it into here, let's see what we get. So if we have a look at the integral of 1 divided by a squared minus x squared dx, and that is equal to the integral of 1 divided by the square root of a squared minus, so x is the a sine theta, so that's going to be a squared sine squared theta. Now, what happens to the dx here now? Well, the dx actually becomes the following. So that means dx is going to be a cos theta d theta, right? So now, if we put this in as well, then what we actually obtain here is, so we have a cos theta d theta, right? All right, so now we see that we could actually common factor out the a squared and this a squared here. So by doing so, we have 1 divided by the square root of a squared, 1 minus cos, or sine squared theta, and that's a cos theta. D theta, I'll put it down here. Okay, so let's see that, well, we see this part down here, the 1 minus sine squared theta. This is also the same as cos squared theta by Pythagorean's identity. right? So that means we could change this. So that means we have 1 divided by the square root of a squared cos squared theta. Then we also have a cos theta d theta. And then this is equal to, well, the square root of the denominator is just going to be a cos theta. So we have 1 divided by a cos theta multiplied by the a cos theta that's out here, d theta. So we see that this a cos theta cancel out each other. And so that means we would just get the integral of d theta, which is just going to be the theta here, plus c. But what is theta? Well, we found theta up here, which was supposed to be the sine inverse of x over a. So if we just put that back in, our integral is going to be, or the answer to the integral is going to be sine inverse of x divided by a plus c. And that is going to be the answer for this integral here. All right. So that was an interesting process that we took. So we see that we actually made a substitution for x rather than doing a u substitution here instead. So whenever we're working with trigonometric integrals or substitutions, it's best to make a substitution for x so that we can make it into a trigonometric function. All right. So let's have a look at the next part. So suppose we want to determine the area of a circle. So we can technically accomplish this by integrating the function for a semicircle. So if we visualize this, so this is the semicircle. All right, this is bad. So if we can actually find the area of the semicircle first, and then we find the area of the circle underneath it, because, well, as we recall, if we take the integral under the positive side and the negative side, the area underneath here, so this is the positive area, this is the negative area, that's going to end up being 0, which is something that does not make sense. We want to know what the area of this circle is. So that's why we had to work with the semicircle first. And the semicircle has a radius of r. Okay, so starting with the equation x squared plus y squared is equal to r squared, we can rearrange it to get the equation of a semicircle. So this is the equation of a semicircle. And then we can take this integral and evaluate it from negative r to r, because that's the lower bound and upper bound for the x ranges. Okay, so let's start by thinking about the substitution here. So this looks like a similar one to the one that we had a look at in the previous example, where we had a squared minus x squared, but instead here we have r squared minus x squared. So we're going to make the same substitution. So we're going to say, so let x be r sine theta. So that means dx. So I'm going to save this, r cos theta d theta. And as well, theta here is going to be sine inverse of x divided by r. All right. So if we also draw the right angle triangle once again, because it's always helpful. So we would have the x here, we have the r, this is our angle theta, and this is the adjacent side, which is the square root of r squared minus x squared. Right? Okay. So if we have a look at the right angle triangle, we can conclude that, well, cos theta then is simply just going to be So that's the adjacent, which is the square root of r squared minus x squared. And this is divided by the r. So that we could also say that this is also equivalent to r cos theta, which is also equal to r squared minus x squared. Okay, so that means we could actually just go ahead and make this substitution into here. All right. So let's go ahead and put the stuff in. But first of all, note that we're integrating from negative r to r with respect to x, but we want to change it to with respect to theta. All right. So let's change the bounds here. So we say that when x is equal to negative r, so that means, so theta, which is the sine inverse of x divided by r. So we have theta is sine inverse of negative r to r, which gives you sine inverse of -1, which then becomes theta is negative pi over 2. All right. And similarly, when x is equal to r, we have that theta, which is equal to sine inverse of r divided by r. So that means theta sine inverse of 1, which turns out to be just pi over 2. So that's going to be our new bounds here. All right, so going back down here, so we had the integral from negative r to r of the square root of r squared minus x squared. Okay, and then dx. So we found that r cos theta was going to be the square root of r squared minus x squared. So that's going to be this part here. We found that the bounds here were going to be the lower bound negative pi over 2. So that's going to be this one. And then theta being pi over 2 being the upper bound. So this one. And then we also found that dx here was going to be r cos theta d theta. So this is going to go here. All right. So let's put everything in. So we have the integral from negative pi over 2 to pi over 2 of r cos theta multiplied by r cos theta d theta, or that also simplifies to the integral from negative pi over 2 to pi over 2 r squared cos squared theta d theta. And well, the r squared here is a constant, so we could bring that out. So we have r squared times the integral from negative pi over 2 to pi over 2 of cos squared theta d theta. All right, so if we want to evaluate this integral, the cos squared d theta, this was actually one of the integrals that we had a look at previously. So it was when we have a cos squared theta. Okay, so cos squared theta, we use one of the trig identities, the one of the half angle identities here. So it's actually this one, this example here. So we changed it to 1 plus cos 2x divided by 2. So let's go ahead and put that in. So what we have here is just going to be r squared multiplied by the integral from negative pi over 2 to pi over 2 of 1 plus cos 2 theta divided by 2 d theta. And we can just go ahead and evaluate this integral. So this would just give you r squared multiplied by the integral of half theta plus 1 over 2 sine 2 theta. And this is still evaluated from negative pi over 2 to pi over 2. All right. So now, or no, this should be 1 over 4. Yep. So now let's put the values in. So we have for the first bound, the upper bound. So we have a half theta and then we multiply by pi over 2 plus 1/4 sine 2 times pi over 2. And we subtract this from 1/2 times negative pi over 2 plus 1/4 times sine of 2 times negative pi over 2. And so there's some terms that we could actually cancel out, in particular this one and this one. So what we just get on the inside part is just going to be, well, the first one's going to be pi over 4. The second one's also going to be pi over 4, so plus pi over 4. So that's r squared, which is equal to pi multiplied by pi over 2. And so that means pi r squared divided by 2 is the area of the semicircle. So that's the area of a semicircle. So now what we want to do, if you want for the area of the circle, we have to multiply it by 2. So that means we have 2 times the integral from negative r to r of the square root r squared minus x squared times dx, which we found to be 2 times pi r squared divided by 2. That's going to be pi r squared, which is indeed the area of the circle there. So we have shown that the area of the circle is pi r squared. And now we're good. So let's move on. So we can use these trigonometric substitutions for the following situations. So the first one is the one that we had a look at earlier. So we have the expression of a squared minus x squared. So whenever we have this expression, what we're going to substitute is x is equal to a sine theta. And the domain for this, well, that's just going to be negative pi over 2 less than theta less than pi over 2. Next, the identity that we would use in a trig substitution like this is the one that we used up here. So that's this part over here. So we're going to use the Pythagorean identity. So we let cos squared theta, which is equal to 1 minus sine squared theta. So that's for the first row. Now the second row, what the next expression we could use is this one. So we could have, instead of a squared minus x squared, we could have x squared plus a squared. So that's by Pythagorean theorem. So that means the substitution that we're going to be using here is just going to be x is equal to a tan theta. And we would have the substitute, and the domain for this one would also be the same. So we have negative pi over 2 less than theta and less than pi over 2. Then the substitution that we're going to actually, or the identity that we're going to be using in this case, is going to be the Pythagorean identity, but for the tan and the secant. So we're going to have to be using this identity here. All right. And as for the last one, we're going to be explaining about the x squared minus a squared. So for this one, we're going to be, well, substituting here, instead of a sine theta or a tan theta, we're actually going to be substituting for a secant of theta. And the domain for this case is, well, going to be between 0 less than or equal to theta less than equal to pi here. However, we cannot let theta be pi over 2. Because if we put pi over 2 in, this becomes undefined. All right. And lastly, so the substitution that we're going to be making here is going to be this one. So we have secant squared theta minus 1 is equal to tan squared theta. Okay, so I'll try to give an example of these ones. So if I draw a right angle triangle, so let's say for the first one, then the opposite is going to be the x, the adjacent is going to be, or the hypotenuse is going to be the a. This is our theta. Then our adjacent is going to be the a squared minus x squared. So that means our substitution is going to be the a sine theta. And so that also means that, well, dx is going to be your a cos theta d theta. Your substitution for the second row is going to be dx is a secant squared theta. And as for your third substitution, you're going to be using dx is a secant theta tan theta d theta. So for this one, well, the second row, this is your right angle triangle that you should construct. So we have the tan ratio, which is the opposite. So if this is our angle theta, opposite is going to be this x, the adjacent is going to be the a here. So by Pythagorean theorem, we have x squared plus a squared. All right. And as for the third triangle, that's a poor triangle. We would have, so if this is our angle theta, we have a right angle triangle. The opposite here, or since secant is actually going to be the hypotenuse over the adjacent, so the hypotenuse here is actually going to be the x. And the adjacent is going to be the a. So that means this part is going to be your x squared minus a squared. So those are the three cases here with the right angle triangles. So let's have a look at an example here. So the next example we'll have a look at is the integral of the square root of x squared minus a squared divided by x to the fourth. So this is following the third row here. So what I'm going to do is I'm going to say, well, let x be equal to a secant theta. So that means d of x is going to be a secant theta. I'll move this down here. Tan theta d theta. So that means, well, secant theta, if secant theta is going to be x divided by a, well, that also means that if I actually want to make a substitution for this one, I could use either the sine ratio, or I could also use the tan ratio here. So if I say, well, let's use the tan ratio. So that means tan theta is just going to be the square root of x squared minus a squared divided by a. Or that also means that a tan theta is also equal to the square root of x squared minus a squared. So I actually just saved some time here, because if I use the right angle triangle that I've constructed here, it's easy to make a substitution for anything that is under the square root here, because here, if I just rearrange the variables, this a comes to this side, we have an expression for x squared minus a squared, which is just going to be a tan theta. So compared to the first example, we didn't have to go through this step and manipulate the identities here. So we just skipped some steps here. All right, so let's go ahead and put that in. So we have the integral of the x squared minus a squared, whole thing square rooted, divided by x to the fourth d theta dx. So that means the integral of a tan theta divided by, so the x to the fourth is actually going to be our a to the fourth secant for a theta, which is then equal to, or you also multiply by dx, which is then going to be a secant theta tan theta d theta. All right. So we could simplify things a little here. So we can, well, simplify the a's here. So this becomes a 2. We can cancel out the secant here and the secant. So this becomes a 3. And so the tan here and this tan could also join to become 1-tan ratio, but it's going to be squared. So that means over here, we could rewrite this as tan squared theta divided by a squared secant to the third theta d theta. All right. So what we can now write, well, let's rewrite the sine, or let's rewrite the tan as sine squared over cos squared, and let's rewrite the secant as cos squared. So now what we have, so if we have sine squared, I'm going to bring the 1 divided by a squared out here. So if 1 divided by sine squared theta divided by cos squared theta and multiplied by cos cubed theta, all this d theta, well, we see here that this cos squared theta, and we would just have one sine or one cosine left. So this is just 1 divided by a squared times the integral of sine squared theta cos theta d theta. Well, this one is just going to be one of our trig substitution or trig integrals here. So we're going to make a substitution for sine squared theta. So I'm going to say let u be equal to sine theta. So that means du is going to be cos theta d theta. And so now I have 1 divided by a squared multiplied by u squared. And the cos theta d theta is just going to be our du here. So evaluating this integral, we would just have 1 divided by a squared multiplied by 1 divided by 3 u cubed. So that, and then plus c. So that becomes 1 divided by 3a squared. And the u, so if we put that back in, becomes sine cubed theta. But since sine cubed theta, according to our triangle, right angle triangle, sine is defined as the opposite divided by the hypotenuse. So we could actually substitute sine here to make it actually, so we have 1 divided by 3a squared, multiply that by the square root of x squared minus a squared, divided by x, all of this to the third power. And we are done with this problem, except add the plus c to the end. All right. So that's for this one. And for the next one, let's have a look at this one, which also looks similar. So let's draw a right angle triangle. So this one, we see that we're going to have to use the tan substitution for this problem. So this is theta. So x divided by a. So I'm going to say let theta, or let x be a tan theta. So that means tan theta is x over a. So according to our triangle here, that's what we should have. So let me write this as the square root of x squared plus a squared. So that means now, if we try to find a expression for this one here, we could actually go ahead. No, that won't quite work. Or maybe it can work, yeah. So if we know that, well, we could do secant ratio here. So I'm going to do the secant. So secant theta is going to be the square root of x squared plus a squared divided by a. And then I'm going to square this side as well. So that means secant squared theta is x squared plus a squared divided by a squared. So that means a squared times secant squared of theta is going to be x squared plus a squared, which is the one that we needed. So this expression becomes the a squared secant squared. And also note that, well, dx here is going to be your a secant squared theta, d theta. All right, so let's go put that in. So we have the integral of 1 divided by x squared plus a squared dx. Put everything in. So we have the integral of 1 divided by a squared secant squared theta and dx, which is now a times secant squared theta d theta. So we see that the secant squared cancel, the a and one of the a's cancel. So we just are left with the integral of 1 divided by a d theta. And lastly, so this is just going to be 1 divided by a times d theta plus the c. And then, so theta, we know that's going to be the tan inverse of x divided by a plus c. And this is actually an important integral that we should keep in mind here. So this is a very important integral that we will be using later on. Okay. So let's try to find the area enclosed by the hyperbola from x is equal to a to 2a. All right. So if we want to find the area enclosed, let's find the expression for y first. Okay. So let's find a common denominator. So if we find a common denominator, which is a squared plus and b squared. So first we have x squared, a squared minus y squared, b squared, which is equal to 1. So that means x squared or b squared, x squared, minus a squared, y squared, divided by a squared, b squared, is equal to 1. Okay, so that means b squared minus x squared, or b squared x squared minus a squared y squared, is equal to a squared b squared. Now I have to bring the x to the other side, so that means I have negative a squared y squared, a squared b squared, minus b squared x squared. And then divide both sides by a squared, negative a squared. So that means I would just have y squared, which is equal to b squared divided by a squared of x squared minus, that's just going to be b squared here. All right, so now we could work on this part here. So that means if we want to find the area enclosed of the hyperbola, so that would look something. Okay, so then take the square root on both sides. So I'm only going to be focusing on the positive square root because I only want to find the area of the upper half of it. So that's the expression here. So this, keep in mind, is only the upper half or the upper hyperbola. So that means now, so if we take the integral now, and we want between a to 2a of this expression, well, okay, so this is going to be a little bit tricky, but let's try to make sure we're doing this right. Or let me try to get this in terms of x, just x by itself here. So if I divide common factor out to b squared divided by a squared, then that means I'm just going to be left with x squared minus 1, just a squared here. So that, yeah, okay. So I could actually rewrite this as the one that I just common factored out. So I have b squared divided by a squared, x squared minus a squared. Or that's also equal to y is equal to b divided by a square root x squared minus a squared. Okay, so that's the upper half of the hyperbola. So we also want to find the integral from a to 2a of b divided by a of the square root of x squared minus a squared dx. So same stuff. We're going to be doing the substitution for the secant one. So let's say we have a right triangle. So for the secant substitution, so we're going to say let secant or let x be the a times secant theta. So that means secant is going to be equal to the hypotenuse divided by the adjacent. So that means this side is going to be x squared minus a squared. So that means dx is then going to be a times secant theta tan theta d theta. Okay, so let's say we want to find an expression for x squared minus a squared whole thing square rooted. Well, note that the tan ratio can give us that. So remember that tan theta is also equal to the square root of x squared minus a squared divided by a. So that means a tan theta is also equal to the square root of x squared minus a squared. So making that substitution and substituting everything else as well, we also need to know the bounds as well. So when x is equal to a, so we had to find theta. So keep in mind that theta is the 1 divided by cos inverse of x divided by a. Okay, so when x is equal to a, then that means theta is equal to 1 divided by cos inverse of a divided by a, which is equal to the 1 divided by cos inverse of 1, which is just going to be 0. And similarly, when x is equal to 2a, then that means theta is going to be 1 divided by cos inverse of 2a divided by a. So that means cos inverse of 2 then. Okay, that is a problem because the theta cos can only be ranging from 0 to pi over 2. Okay. Let's see. So cos inverse of 2. 1 second. Yeah, so this one actually has no solutions to it. So let me go ahead and change that value to make it defined. Okay. Let me make it this into, so instead of from a to half of a, I'm gonna make this from half of a to a. Because if I do half of a, then I could also say that, well, this is just going to be a divided by 2a, cos inverse of 1/2, which is just going to be pi over 2, or pi over 3. So that means it's going to be 3 divided by pi. So that should be a bit easier now to work with. Okay, so now let's go ahead and put everything together. So the bounds are going to be changing. So we have the integral from 3 pi divided by pi to 0 of b divided by a. The square root is going to become a tan theta. The dx is going to be a secant theta tan theta d theta. So now this is just going to be the integral from 3 pi to 0, and we could just get b tan squared theta. Oh, so we still have an a as well. So this is going to be ab. So we have tan squared theta secant theta d theta. Okay, so this is going to be one of the trig integrals that we have talked about in the previous lesson. So this rule will actually be for when m is odd. So we're going to use the second rule here. So we're going to substitute, or sorry, this is for when m is odd. So let me go back. So tan squared, I could also write this as the integral from 3 divided by pi, 0. I'll bring the constant ab to the outside. So this is also the same as saying, well, secant squared minus 1 of secant theta d theta. That's ab integral 3 divided by pi of 0. So that's secant cubed theta minus secant theta d theta. Well, the integrals here we have already computed before. So secant cubed theta we computed, which turned out to be this entire integral here. So I'll actually just copy that. So that's going to be secant theta, secant x tan theta. Oh, so that is equal to AB times, so that's going to be secant theta tan theta plus the ln of secant theta tan theta plus tan theta, all this divided by 2, and then minus the ln of secant theta tan theta. And let me make sure that is correct. So let me go back, double check this. Yeah, and so we found this integral before, and we found this integral before. So yep, I got both the integrals here. So I'll leave it as an exercise for you to actually compute this value from 3 divided by pi to 0, since I'm running out of room here. All right, so compute the value is just going to be left as an exercise for you. Okay, so let's have a look at the next concept. So let's have a look at the concept of integration of rational fractions functions by partial fractions. So when we're integrating rational functions, it is often easier if they're broken up to the sum of simpler rational functions. So if we add these two rational functions, so let's simplify this. So we get 3. So if we want a common denominator, we multiply the first term by x plus 1. So this one becomes multiply x plus 1 and multiply x plus 1. And for the second one, I'm going to multiply by 2x minus 1 and multiply by 2x minus 1 here. So that means 3x, 3 times x plus 1 minus 2 times 2x minus 1. All this divided by 2x minus 1, x plus 1. So that means we would just get, well, 3x plus 3 minus 4x plus 2. All this divided by 2x minus 1, x plus 1. So we would just get negative x plus 5 divided by 2x minus 1, x plus 1. So now if we actually try to integrate this, so we integrate negative x plus 5 divided by 2x minus 1, x plus 1 of dx. So that means I could break this up. So I could change this back into this expression here. So that means if I change this, the integral minus 2 divided by x plus 1 of dx. So that means I could just integrate each of one of them. So for first one, I'm just going to have the integral of 3 divided by 2x minus 1 dx minus the integral of 2 divided by x plus 1 dx. And this could just be the simple ln expression. So keep in mind that the first integral, since we have a 2 here, so we're going to actually have to divide it by 2 as well. So divided by 2 ln 2x minus 1 plus minus 2 times the ln of x plus 1 plus c. So that's the integral for this one. But if we're evaluating integrals of the form px divided by qx, where p and q are both polynomial functions, the first step is to divide the rational expression if the numerator is great. The degree of the numerator is greater than the degree of the denominator. So, for example, if we want to divide this polynomial expression or this polynomial on the top by this binomial, what we just have to do is, well, apply long division. So this be x divided by 1, x cubed plus 0x squared plus 2x plus 1. So if you remember from maybe advanced functions, we have to see how many times the x can go into the x cubed, which is going to be x squared times. So that means if I multiply this out, subtract x cubed plus x squared, all this divided. So we see x cubed cancels. And so we would just have negative x squared. So how many times does x go into the negative x squared? Well, negative x times. And so that means if I multiply this out, I also have to bring this down. So I have negative x squared minus x. And so if I continue this, I would just get 3x plus 1. So how many times does the x go into the 3x? Well, just 3 times. So that means if I subtract the 3x plus 3, I would just get, so the 3x cancel, and it would just be left with the remainder of negative 2. So that's why we would have to use long division to make our work a little bit easier in this case. All right, so the second step here is to factor the denominator q of x. So any polynomial can be factored as the product of linear factors and irreducible quadratic factors. All right, so let's say we want to factor this expression over here. So note that there should be a plus here. So we could first of all group these two terms and these two terms together. So for the first one, we could, well, common factor out the x squared, and we would have the x plus 1 out here. As for the second one, or actually, sorry, no, this is not by grouping. So this one you actually had to do by long division as well. So we could see that I could factor this into x plus 2 and then expand x cubed or x squared minus x plus 3. If you expand all this, you should be able to get the polynomial that we have up here. Okay, so that's something you could try on your own. And then the third step is to express the rational function as a sum of simpler rational functions. So of the form p of x divided by q of x. So if this is the rational function, then I could write this as f of x divided by g of x plus h of x divided by k of x, and maybe so on. So that's the process that we would need to do to apply partial fractions here. So there are 4 examples that we will have a look at for evaluating rational integrals of rational functions. Okay, so for the first case, let's say that the denominator is a product of distinct linear factors, and we wish to evaluate this integral over here. Well, by distinct linear factors, we mean that since the degree of the polynomial of the denominator is 3, we should have 3 linear factors here. So let's have a look at the denominator. So first observe that, well, x cubed minus 2x squared minus x plus 2 is also the same as saying, well, x squared x minus 1 or x minus 2 subtract x minus 2. So that's also the same as saying x squared minus 1, x minus 2. So that's also x plus 1, x minus 1, x minus 2. So we have 3 distinct linear factors. All of these are different. So that means I could write the rational function as 2x squared plus 2x minus 6 divided by the distinct factors of x plus 1, x minus 1, and x minus 2. Now what I'm going to do is if we want to write this as individual rational functions, so we have to know what these values are. We cannot just assume. So let's say we let a, b, and c be some numbers such that we could have this so a divided by x plus 1 as one of them, plus b divided by x minus 1, and then plus c divided by x minus 2, where the a, b, and c are the terms that we need to find out. Okay, so over here now, if we find a common denominator, which is just the product of these 3, so that means we would have to multiply x minus 1, x plus 2, plus b times x plus 1 times x minus 2, plus c times x plus 1, x minus 1. All this is divided by x plus 1, x minus 1, x minus 2. So if I expand the binomials, so I have x squared minus x. Oh, so this should actually be minus. So that's minus 3x plus 2 plus b times x minus x, or x squared minus x plus 2 minus 2 plus c times x squared minus 1. all this is divided by x plus 1, x minus 1, x minus 2. So that means if I expand it once again, ax squared minus 3ax plus 2 plus bx squared minus bx minus 2b plus cx squared minus c. And all that is divided by x plus 1, x minus 1, x minus 2. Now what I'm going to do is I want to make sure that I could write in terms of this expression here. So notice that we have coefficients 2, 2, and negative 6. Well, I could also do the same with the terms that I have here. So I could say that, well, I could group the coefficients. So say, for example, I have this ax squared here. I have this bx squared here, and I have this cx squared here. Well, I could write that as a plus b plus c multiplied by x squared. So that means this number here, this a plus b plus c, has to be equal to this number 2 over here, right? And similarly for the other terms as well. So for example, the x term, we could have the negative 3ax, you have the negative b, and that's all. So we're going to have the negative 3a minus b times x. So that means the negative 3a minus b has to equal to this 2 over here. And lastly, it's just going to be the constant numbers. This should be 2a. So I have 2a minus 2b minus c, which is the constant term. And all this is divided by x plus 1, x minus 1, x minus 2. So I'm going to highlight the last one. So I have this constant, this constant, this constant becomes this constant. And this constant here has to equal to negative 6. So now we just need to compare the coefficients. So we see we could have a system of equations given by a plus b plus c, which is 2, negative 3a minus b, which is this 2, and 2a minus 2b minus c is negative 6. So let's write this. So we're going to compare the coefficients. So for the first equation, we have a plus b plus c, and that is equal to 2. The second one, I have negative 3a minus b. This one's equal to 2 as well. And then the third one, I have 2a minus 2b minus c. This is equal to negative 6. Okay, so now let's try to solve the system. So we call this equation 1, call this equation 2, call this equation 3. So I'm going to add the first equation and the third equation so if I do 1 plus 3, then that means I would have 3a minus b, and this is equal to negative 4. So I'm going to call this equation now equation 4. Now I'm going to add equations 2 and 4 together. So then I could just have negative 2b to be equal to negative 2. So that means b is going to equal to 1. And now I'm going to substitute this into 2. So that means it's negative 3a minus 1 is equal to 2. So that means negative 3a is equal to 3. A is equal to negative 1. And so that means by 1, that means we would just have negative 1 plus c is equal to 2. So that means c is equal to 2. So we have the three coefficients, a, b, and c. So we have a being negative 1, b being 1, c being 2. So let's go ahead and put that into the rational function now. So back to this part up here. We could write this. So down here, we have the original integral given by 2x squared plus 2x minus 6 divided by x cubed minus 2x squared minus x plus 2 dx. So I could also write this as the integral. So the first one is going to be a divided by x plus 1. So a was -1. So I have -1 divided by x plus 1 dx plus the integral of b divided by x minus 1. So that's going to be 1 divided by x minus 1 plus the integral of 2 divided by x minus 2 of dx. And then we integrate, so that would just be negative ln x plus 1 plus the ln x minus 1 plus 2 ln x minus 2 plus c. And that is the integral here. Okay. So I will continue on with the partial fractions in the next video. There are about 3 more cases that we will be exploring before we move on. So this part is a good place to stop for today. So if you guys have any questions, just feel free to let me know in the comments down below. So I'll see you guys in the next video.